ITC Special Colloquium. Today's speaker is Rainer Weinberger. He's a PhD student in Heidelberg. He just defended his thesis last week. He will be talking about modeling AGN feedback in galaxy scale simulations. And I should also mention that he has an offer from the ITC, so please talk to him and convince him to come here.
Okay, thank you. Thanks everyone for showing up. As Raoul said, my name is Rainer Weinberger. I'm a PhD student at the Heidelberg Institute for Theoretical Studies, meaning I did my PhD with Volker Springer mainly, but also with a lot of other people, as you can see here. Also people that are currently at the ITC, and a lot of people that have been at the ITC at some point. And what I mainly want to talk to you about today is the feedback from supermassive black holes, and in particular in the context of galaxy formation, which was the topic of my PhD. So I will briefly introduce AGN feedback from this galaxy formation perspective. Then I will go over to very large-scale simulations, cosmological volume simulations, and in particular the IllustrisTNG project, like some people here are involved in. And I was substantially involved in the modeling of the supermassive black holes, their growth and their feedback effects on the galaxy population. And I will then also be talking about these effects, observables you can deduce from them, and what you can actually learn from these kind of simulations about AGN feedback in general. But it turns out that looking at this is actually not really sufficient to get the real nature of AGN feedback and to understand the real nature of AGN feedback. And to get a bit of better handle on this, I will talk a bit about more idealized high-resolution simulations that I have been doing, and I'm actually still doing, so this is an ongoing project. In a particular type of systems for a particular type of AGN feedback, namely AGN-driven jets, and open questions in this regime. And then we'll discuss briefly also what future research I think would be important to be, or what we should be doing, and what I will be doing also in the next couple of years. So let's get started with that. First of all, what is actually the need for AGN feedback if we look at a galaxy formation from a galaxy formation theory point of view? So that supermassive black holes exist is simply not enough of a justification in this context. So already a paper, one of the early papers here by Crotin et al. 2006, introduced this, or actually has it in the title, 3 problems that we are actually able to solve in galaxy formation by invoking feedback from supermassive black holes. The first one is the galaxy luminosities, or in particular here the galaxy luminosity function, here the K-band luminosity, and in particular the bright end of the galaxy luminosity function, where you can see here a prediction from theory, in this case a semi-analytic modeling, without invoking any kind of feedback from supermassive black holes, and here with invoking feedback effects from these supermassive black holes, matching the data far better. A second thing that we can observe and we can explain by invoking these feedback mechanisms are colors of galaxies. So you have here a measure of color, in this case U minus I, but you could have any other as well, versus stellar mass. And in black here you have data from the SDSS survey, so a lot of galaxies here. And you can see a clear bimodality of galaxy colors in the observed galaxy population, and a transition from this so-called blue cloud of galaxies to a red sequence of galaxies at characteristic mass of around a few times 10 to the 10 solar masses in stars. And you can actually reproduce this by now reasonably nicely invoking AGN feedback. And we know that without AGN feedback, you would essentially just get this blue cloud here and no red sequence. A third thing that I also find particularly interesting is when you look at the most massive systems in the universe, looking at galaxy clusters, and in particular they are looking at the gas properties instead of the stellar properties. You can access that in the X-rays, and you can deduce a central cooling time, which is plotted here in a plot from Dunn and Fabian 2006, versus the radius from the center of the galaxy cluster. And the main point here is that these cooling times decrease significantly, and in particular below a gigayear or a few gigayears, which means that we would expect significant cooling flows to happen in these galaxy clusters, but we do not really observe these. So these are three justifications, or from a galaxy formation viewpoint, why we need AGN feedback, and I hope I can convince you in the following that we're actually able, with some recipe of AGN feedback, to solve these three problems simultaneously. So why is this still a controversial topic in general, or an unclear topic? This is mainly in galaxies, it's very hard to see or probe AGN feedback. So what you can see, what you can observe, is, for example, radio emission here in a paper from Baldi et al. 2015, where they found very, very centrally peaked radio emission. And you can also look at the host galaxies and see that these radio-emitting galaxies, the difference here between the colors is not so important, but they mainly occupy here a color versus stellar mass in the other direction, unfortunately. This red sequence and the so-called green valley, which is thought to be a transition region towards the red sequence, while they are not really present in actively star-forming galaxies, which have a blue appearance. So this is more of an indirect evidence that this AGN feedback might actually play a role there. A second, slightly more direct detection of that is to actually probe the gas dynamics in galaxies directly here via integral field spectroscopic surveys. But this is relatively recent work by Chirong et al. 2016, so that's the MANGA survey, where they traced gas outflows, AGN-driven gas outflows in H-alpha, and were actually able to identify these. But these are very recent recent observations. And the second thing is, like, you have proven, assuming that this all is correct, you have proven that the AGN does something with your gas, but you haven't really proven that the AGN is responsible for reducing the star formation rate itself. So in this sense, in galaxies, it's very, very difficult to have a direct evidence of AGN feedback. In galaxy clusters, however, this is a slightly easier task, and it has been done here. A nice review from Fabian et al. 2012. So you have galaxy clusters, and you can plot here the central cooling time. I showed you the cooling profile, essentially. You can then just plot a histogram of the central cooling time of local galaxy clusters, and have here essentially color-coded. So the black ones are those who show these kind of low or X-ray dark spots slightly off-center, which are thought to be cavities inflated by AGN jets. And these, here's a second generation of these cavities buoyantly rise in the galaxy cluster atmosphere. And all the black histograms here is essentially the galaxy clusters that show these signatures, while the white ones are the ones where we don't show the signatures of AGN activity. So you can see that whenever you have a low central cooling time, that means when you actually would expect a significant cooling flow, you also have associated energy input from the AGN, which counteracts the cooling via the X-ray radiation. And you can do even more than that. You can estimate here the energy that was injected by a jet, or the average jet power, which is plotted here on the y-axis, and plot this versus the bolometric luminosity of the respective galaxy cluster, and what you get is almost a one-to-one correlation. That means the heating energy in an individual galaxy cluster approximately matches the cooling energy from the gas in that galaxy cluster, which I think is one of the strongest indications that the AGN feedback is actually at work here. But how exactly this is then distributed is also still unclear. Yeah.
What is the spatial scale on the image? How far away
Here?
do you see those gaps? Yeah.
Well, it depends. It's very, very, very different from galaxy cluster to galaxy cluster. But these here are usually a few tens of kiloparsecs in the scale. That's Perseus. It can be larger. So this is all talking about the centers of galaxy clusters, I should say. The outskirts are not so important, but the cooling time is just very much larger. So going to simulations of galaxy formation or of galaxy theory in general, there have been usually two types of feedback from supermassive black holes that have been invoked in the past. One here, for example, a paper by Di Matteo, Springel, and Turnquist, that invoked a feedback effect from luminous AGN, so-called quasar mode feedback, that is likely triggered whenever you have a lot of gas falling into the central region and accreting onto the supermassive black holes. So if a very luminous supermassive black hole, and if you assume some coupling efficiency of the radiation from the quasar onto the surrounding material, you get a significantly different post-merger outcome. In particular, you always get some kind of starburst usually during a merger, but you kind of continue with the same star formation rate without any supermassive black hole feedback. While with this quasar mode feedback, the star formation rate might be significantly decreased due to a blowout of gas just by radiation pressure. So that's one mode of feedback. A second mode, which is usually called the kinetic mode, or well, this is a historic term, radio mode also, because it's usually or largely associated with radio emission, is a mechanical feedback that is happening, for example, in galaxy clusters, as I just discussed. So this is a mode which is usually identified with collimated or uncollimated, mostly collimated outflows from very high mass supermassive black holes in very high mass halos, meaning mostly also in galaxy clusters where you can actually see it best. And here, for example, a simulation by Dubois et al. 2010, though many other people have worked on that as well, shows that invoking this kind of feedback mechanisms in a galaxy cluster simulation, you can actually reduce the star formation rate in a galaxy cluster significantly. And I don't have observations on this plot, but I can tell you that this is definitely way higher than you would have in any realistic galaxy cluster that is observed. So, having introduced these parts of these different types of supermassive black holes, I would like now to introduce the IllustrisTNG simulations, which is a large-scale cosmological volume simulation following essentially the philosophy to simulate a representative part of the universe and including all physics that we believe to be crucial for galaxy formation and trying to reproduce a realistic galaxy population. So this is now essentially the second part, or the second generation of this kind of simulation. The first one was the Illustris project, led by Mark Vogelsberger. And we have improved the model, in particular the model of supermassive black hole growth and AGN feedback. But there are also a lot of other models that need to be included in these simulations, like models for star formation, stellar feedback. You need radiative cooling. What we also have included here and not in previous generations are magnetic fields in the entire simulations. And we've significantly extended the scope of the overall simulation project, and it's actually still ongoing, so this box is not yet finished. mainly, what's interesting here and for this talk is that we have a significantly larger volume that we are simulating in one of the boxes, which means that we probe way more into the galaxy cluster regime, which is, as I already indicated, a quite interesting regime for AGN feedback or for testing AGN feedback. And I'll come to that in a bit. So I'll just briefly mention then the model for AGN feedback we're using in these simulations as far as it's needed for the interpretation of the results. So we do have these two modes of AGN feedback I told you about, namely for low mass and high accretion rate black holes, here being the accretion rate relative to the Eddington limit, here the black hole mass. So everything that is in red here is in the so-called quasar mode, or modeled as a thermal injection of energy, going actually back to an implementation that is already used by Springel, Di Matteo, and Turnquist 2005. While at the high mass end and at low accretion rates, we have a new pulsed kinetic injection of feedback energy, which models this so-called kinetic mode, mostly then consequently in massive galaxies and galaxy clusters. And this is actually a new implementation from 2016-17 roughly that I also worked on a lot. The main idea how this works is that we have a randomly selected direction where we give kicks to the gas surrounding a supermassive black holes on kiloparsec scales. That's the resolution limit of these simulations. And what this includes, or what this induces, are shocks and a bit of turbulence in this in the surrounding medium at a very centralized object. So what I should say here is what we are not modeling are really large scale, tens to 100 kiloparsec scale extending jets from AGN. I'll come to this in a minute. So the motivation for doing this are essentially recent theoretical studies, both of magnetocentrifugally launched uncollimated winds that are supposed to be there and are supposed to be quite energetic, according to a study here by Yuan et al. 2015, as well as a recent study by Mukherjee et al. 2016, studying collimated but rather low power AGN jets interacting with a rather clumpy interstellar medium, concluding that most of the feedback energy or the energy of the jet is actually deposited very locally, meaning the central few to 10 kiloparsec within to the center of the host galaxy. So we have a very centralized heating here. So to give you a bit of an idea of when these different feedback effects are actually important, what I plot here is the energy injection rate in different feedback channels: stellar in green, thermal AGN feedback in red, kinetic AGN feedback in blue, for galaxies in the simulation, binned in bins of final stellar mass, here from rather low mass systems to Milky Way-like systems, a bit more massive systems, and even more massive systems here. So one thing you can notice here is that this green line, meaning the stellar feedback, always dominates at high redshift. So in the x-axis here is a plot redshift. And at some point, in particular for the more massive galaxies, the feedback from supermassive black holes actually takes over in terms of the energetics. This is true for almost all galaxies, maybe the least massive galaxies not, but for the rest of the galaxies. The kinetic AGN feedback, on the other hand, just kicks in quite late actually, but then takes over the global energy budget in galaxies that are more massive than 10 to the 10.5 or a few times 10 to the 10 solar masses. So this mass scale turns out to be actually quite important. So coming to a few results of these simulations. So I've discussed previously that these 3 points here are three of I think the key galaxy properties we want to explain by AGN feedback. And I'll show you now in a minute how we are doing on that. So here I actually don't show the galaxy luminosity function as before, but rather the stellar masses of galaxies, but that's quite comparable usually. It just depends on whether you kind of infer that from observations going up all the way to stellar masses, or from the simulation and inferring the luminosities. We'll be using the same models in the end. So what you can see here is that we are actually able, with the complete model used in IllustrisTNG, to reproduce the stellar mass fraction of galaxies from 10 to the 11 to 10 to the 14 solar masses in halo mass quite well. And I should say this is more or less by construction, because this was the goal when we started constructing the model. We were literally looking at to reproduce this quite well. That doesn't mean that this is a trivial task. So people doing these simulations have failed for a decade or so. And it seems like we are now finally reasonably under control. So we are able to get the stellar masses, and consequently also the galaxy luminosity function quite reasonable. The second thing, and you've seen this plot already, this is actually from the IllustrisTNG simulation from a study by Nelson et al. 2018, is the galaxy color distribution, which we are simultaneously then also matching quite well, which means essentially the integrated star formation rate over some period of time needs to be correct, not just the global stellar mass, so the global integrated star formation rate, but more the recent star formation rate. So that's also looking quite good, though there might be some residual issues, but they might also be due to an exact comparison between simulation and observation, which is far from trivial. And the third thing, and I'm consider this as a particular success of the model actually, is looking at the cooling flows, or the central cooling time here of different halos here in the galaxy cluster regime, rather, from few times 10 to the 13 to 10 to the 15 solar masses. And what we are actually able to get here is quite a number of systems here have cooling times less than a gigayear in their centers. Though, and I will come to that also in a minute, there might be fewer here than actually seen in observations. So we might not get everything completely right, but it looks at least that it's roughly consistent. So the main point here is this is all the same model of AGN feedback, and these three constraints are to some degree independent, which essentially tells us that invoking AGN feedback seems plausible at these scales. And there are a couple of more observational constraints, or in general constraints we can think of that we get out of the simulation, and that might tell us something about the model itself. In particular, the growth of supermassive black holes themselves, which I'll show you here. So this is the supermassive black hole accretion rate as a function of redshift for or in different AGN feedback modes, so in the thermal mode, in the kinetic mode, and in black, the growth via supermassive black hole mergers, which is quite interesting to look at, as I will show you in a minute. So what you can see here is for low mass supermassive black hole, that's the redshift 0 mass, 10 to the 7 to 10 to the 10.5, the accretion rate onto supermassive black hole always dominates the growth of these black holes, while for high mass supermassive black hole, 10 to the 9, 10 to the 9.5, and these are the things that live in the centers of galaxy clusters, the thermal feedback actually ceases at some point, and the kinetic feedback kicks in. And what the model does here is that the supermassive black hole accretion rate gets reduced by orders of magnitude, which doesn't mean that the supermassive black holes don't grow anymore, but simply that they don't grow anymore via gas accretion, but via mergers. And this, in turn, means that the growth history is completely different, and that we have to interpret like correlations, for example, between the supermassive black hole mass and the host stellar or stellar bulge mass, or also velocity dispersion, in a bit different way than we used to think about that. In particular, so we have this transition here at around 10 to the 8 solar masses in black hole mass. So the lower half here is where the supermassive black holes were always dominated in growth via accretion. And what we see here is a rather non-linear or non-power law behavior also of this relation. And up here, from 10 to the 8 solar masses upwards, we get a power law here, which is actually close to 1, which is also close to what is observed here, are the observations. These are very uncertain, but nonetheless is quite remarkable. And the only reason why we get this correlation here and not just a blob is essentially hierarchical merging. And this is a bit similar to what has been pointed out here by a paper from Janke and Maggio, saying essentially you can start with whatever shape you want down here. Assuming you have hierarchical merging, you always get a correlation. And this is just what is happening. The only difference between what we get here and this work here is rather justified or criticizing the idea of AGN feedback being responsible for that. For us, it's a consequence of AGN feedback that this process is actually happening. So that is actually very similar to what Graham and Scott suggested in 2013, inferred from observations, essentially. So I found this quite interesting. And the second thing that comes to my mind when I look at these things, I found this really, really surprising when I first looked at that, is actually the quasar luminosity function, which is, for me, from my point of view, the most basic observation of accretion onto supermassive black holes. So the question is now, okay, if I have here a reduction of the accretion rate, do I somewhere have a dip in the quasar luminosity function, or am I completely off in the quasar luminosity function with respect to observations? And as it turns out, we are not really. So the quasar luminosity functions here, the bolometric luminosity, and here just the number density, different observations here in gray and black, and the simulation results in blue. One thing you have to know about these observations is that they are really uncertain at the low luminosity limit, so everything below 10 to 45 ergs per second, I would be really careful about interpretation of these, and you can also see that the different observations, or observational fits, I should say, diverge quite drastically here. And the high mass end of the quasar luminosity functions, however, is reasonably in agreement between observations, and that's also where we agree reasonably well with what observations tell us. So the interesting thing here is that all these supermassive black holes that are actually in this regime of this really efficiently accreting supermassive black holes are actually not the same supermassive black holes that are important for AGN feedback at all. So that's two totally independent things. But on the other hand, the growth itself is important for the supermassive, for the AGN feedback in the end to be important. Because if you didn't have a massive black hole, your energetics would just not work out. So going now to a specific type of systems, namely galaxy clusters, here still in IllustrisTNG. As I told you, we have a significantly larger volume than we had previously, and we are able to probe galaxy clusters up to 10 to the 15 solar mass in halo mass, look at the X-ray properties, look at the stellar properties, and also look at other gas properties, for example, metallicity profiles, and see whether they are consistent. So why is this interesting for AGN feedback in general? Well, mainly because the gas we can actually access through observations, which is the hot intra-cluster medium component, is a volume filling component, and that's accessible And this actually, or properties of this intra-cluster medium change quite significantly if you change prescriptions for AGN feedback. That has been known for a while. Here, an example from Lebrun 2014, that even like really fundamental properties like the gas mass within the entire halo changes by like a factor of a few, depending on what you're doing here. And you have constraints on that, what you would be interested in getting. And we match these constraints reasonably well. However, what we don't match, and that's where things actually become interesting, is the spatial distribution of the gas in a galaxy cluster. In particular, we do not really, or the simulation is here in purple and the observation is here in black. And you see towards the center of the galaxy cluster, the gas fraction, here is a density, is significantly lower than you would expect or you infer observationally. And interestingly here, this looks like almost the same paper. It's actually not, and it's actually also not the same simulation. So these are two completely independent simulations. That one here is from IllustrisTNG, and the other one is the Cluster Eagle project, which is a kind of competing project with a different hydrodynamic method, different AGN feedback prescription and everything, but seems to have this generic problem of not reproducing the central density profiles of galaxy clusters correctly. And this motivates me, or was one of the motivations, to start a new project on AGN feedback in galaxy clusters. And in particular here, I should say, I initially mentioned that the AGN feedback we are using is more or less by construction confined to a very central region. If you look at observations here, like in Cygnus A, that's very extreme, I must admit, but you get the point here best, is like you have jets inflating cavities here, and these are emitting here in the radio, which are shown in red. And these are by no means in the center of the galaxy cluster. So you also probably wouldn't expect the heating from AGN jets to happen in the center of galaxy clusters. And that might just be the problem that we have with our simulations, that we're actually doing something wrong in the modeling of AGN feedback in these kind of systems. And that led me to another project where I tried to model jets, AGN-driven jets, in a galaxy cluster environment with as much resolution as possible. So this is essentially what you get from that. This is a very idealized simulation, but you get the main point, essentially, that you have a jet inflating a cavity which is of very low density. So this is then just driven outwards by buoyancy forces, experiencing some fluid instabilities on the surface layers of the cavities, but in the end not leaving much behind here. And what I want to do here in this project mainly is to investigate how do you actually deposit energy in the galaxy cluster, given that this cavity just rises outwards. So do you actually get a net energy deposition in the galaxy cluster center while the material just flows out? And actually, there are, in this case, magnetic fields in the cavities, no magnetic fields around that. I'll show you an example in a minute where we also have surrounding magnetic fields in the intra-cluster medium. It has very interesting effects, so in a minute. So you can infer from observations here, again, that's a while ago already, from Dunn and Fabian, essentially the needed heating rate as a function of radius for gas within a certain radius from the AGN to locally at every radius balance the cooling losses. And this is shown here for a number of galaxy clusters and massive galaxies. The main point here being that this increases out to 100 kiloparsec and even further. And that is actually also exactly what you get in this simulation. is that the heating rate as a function of radius actually increases up to the position of the lobe, and you also have some effects from a bow shock here, in a very similar manner. So I'm not brave enough to plot this here actually, because this is just one single event, and I wouldn't talk here about a like self-regulated feedback events. It's just trying to figure out whether it's conceptually possible to deposit energy here at all, which actually it turns out to be. And secondly, whether the radial distribution roughly could work out or not. And the conclusion from that is that it actually, there is some energy deposition. This energy deposition, I should say, is not due to the driving of turbulence or things like that, which are or were the favored scenario up until very recently, and also not to a mixing of the material here with the surroundings. But it seems rather like you're inflating the cavity, essentially having the PDV work done on the surrounding gas, which lifts the entire surrounding gas atmosphere. And once the cavity here rises, this gas falls back and actually deposits its energy, then its gravitational energy via falling back into thermal energy in the end. And that's what's heating the galaxy cluster center in this case. It's not clear, however, whether this is sufficient heating, and some observational studies indicate that it's actually not sufficient. So a couple of other scenarios that can be tested with this kind of models is, for example, whether you have other mechanisms to couple feedback energy from jets into the surrounding intracluster medium. So one project that a student I've been working with, Christian Ehlert, has been doing a while, is launching these jets. They're, as I said, magnetized jets, but weakly magnetized, in a galaxy cluster environment with a turbulent magnetic field. And what he also included here is essentially a model for acceleration of cosmic ray protons in the jets. So these cavities in the end will be filled with cosmic ray protons. And these cosmic ray protons have interesting properties. In particular, people think that they are able to propagate with respect to the thermal gas component along magnetic field lines with a certain streaming velocity. And that's what we included here as well. So what you can see then here first in the density is like you have the jet that kind of gets stopped at some point. You get this cavity, which is very underdense. You have here the cosmic rays in there, and you have a magnetic field in and outside. And actually you get here a so-called magnetic draping layer at the outer edge of the cavity, which is moving outwards. So you actually have magnetic fields that bend around the cavity here. In parts stabilize this also. But what is more important for these magnetic fields here, that they bend around in this direction. And as I said, these cosmic ray protons can travel along magnetic field lines, but can't travel perpendicular to them. So they can't really escape the cavity to the outside, but they can escape towards the inside of the galaxy cluster. And that's exactly what's going on here, that cosmic ray protons are essentially lost in the process of a buoyantly rising bubble. And these cosmic ray protons carry quite a significant amount of the energy that was initially injected in the jet, which is an assumption. But first analysis on that shows that the radial heating rate you would get actually matches quite well the cooling losses due to X-ray radiation. And like studies along these lines can also then be done with a lot of other effects that are claimed to be important for AGN feedback in these environments. These include, for example, the presence of substructure in the galaxy cluster. So my galaxy cluster so far had no galaxies, which is a bit embarrassing. And including those would also actually drive significant amounts of turbulence. Actually, some people argue that it's more turbulence due to the substructure than due to any AGN jets or related things. In any case, the morphology of these cavities changes quite significantly, and this in turn will also change the interaction mechanism with the surroundings. A second thing that also affects the jet itself quite significantly is, in the end, cooling, or in particular, a multiphase gas surrounding the supermassive black hole. I showed you this plot already from Mukherjee et al. 2016. So what they find is that this significantly disperses the jet and kind of stops the jet earlier than it would in other ways. But there are also other effects, maybe more interesting physics that might be going on in these galaxy clusters. For example, thermal conduction via electrons along magnetic field lines. And Raoul Cannon here showed in a paper from 2017 that this might lead to a significant changed central gas properties, in particular central metallicity properties, but also thermodynamic properties in the center, mainly because the conditions for fluid instabilities change significantly. And the second thing to keep in mind here also is that the viscosity, the physical viscosity of the gas in a galaxy cluster might be non-negligible, and this might actually have quite a significant effect on the dynamics of gas in the galaxy clusters. And all these effects, I hope that I can probe one by one in the next years. So this is now one specific system where I think we have the best chance also from observations to constrain that very, very accurately. But what I'm also interested in is, well, okay, talking now about galaxy clusters, but they are just the chosen few really massive systems. What about the galaxies? And can we actually learn something about AGN feedback in galaxies and really the nature of AGN feedback, not just the plausibility of AGN feedback in galaxy clusters via this more idealized high-resolution studies? And in particular, what you need to consider there is things like stellar feedback become much more important. In galaxy clusters, you can argue, okay, you have a rather low amount of star formation, so you also have a very low amount of stellar feedback, and you can do really simple order of magnitude estimates that is completely negligible for your studies. But this is no longer the case once you go to kind of massive elliptical galaxies. And I already mentioned that the multiphase structure of the interstellar medium, or in general the gas surrounding supermassive black holes, might have significant impact on how outflows from these supermassive black holes are actually then how they end up at larger scales. And all this, essentially, I hope to put a bit of a theoretical constraint of what actually does it mean to have AGN feedback, what mechanism actually reduces star formation from some outflow. So linking the outflow part, which can be observed, to a reduced star formation rate, which also can be observed. But everything in between we have hard to constrain in observations. So to conclude, I hope I've shown you that efficient AGN feedback is able to explain some, I didn't show all, but there are a lot of observables, but some of the observed properties of massive galaxies and galaxy clusters, and more comparisons to different observables will be upcoming. But I should also say this is all just a plausibility check in the end, because you have a lot of free parameters and you're kind of stuck with these free parameters. So it's very hard to say more about that from these large-scale simulations. And that's why I believe we need more small-scale, more idealized, and more high-resolution simulations. For example, the one I showed you on AGN jets in galaxy clusters, where you can physical effect by physical effect actually probe which effect is the key to understand the interaction between the AGN and the environment. And the main message here, I would say, that we actually have all the tools from a simulation perspective available to do that. So we all these simulations are by today's standard reasonably moderate in computational cost, and actually could be done. Putting this all together is a lot of work, of course, but I think should be done. And for the future, I think the important thing to focus on are the interaction mechanisms between AGN-driven outflows and their surroundings, and really to figure out under which conditions or with which ingredients can you actually have a efficient energy deposition in a gas component that is responsible in the end for star formation. And one other thing that I've been thinking about a lot is what causes the scale at which AGN feedback becomes efficient. And there are a couple of works on that, but I'm not really convinced by them. So there are a lot of problems related to that. In particular, what you need to take great care of in designing a model for AGN feedback in these cosmological scale simulations is that you don't destroy your Milky Way-sized galaxies that seem to be largely unaffected by AGN feedback. But this is also a debated statement. And the third thing that I've been wondering is AGN feedback actually the same in elliptical galaxies and galaxy clusters? And I asked this to several observers, and they all said me essentially that it isn't. But I'm not really sure why it isn't. So figuring out whether this has something to do with either the environment, meaning the galaxy properties, or actually with the AGN properties would be a very interesting thing to say. And with this, I would like to stop. Thank you.
Okay, any questions?
So you said the heating mechanism in your simulations, your jet simulations, was basically gravitational potential energy being added to the gas.
Yeah.
So we know observationally, even though they're hard to detect, that when cavities are inflated, these shocks are driven by the cavity inflation.
Yeah.
And it turns out, even though they don't inject much entropy, if the Dewey cycle is short enough that over many cycles they inject a significant amount of entropy heating into the ICM, or at least in some cases, balance cooling. So in your simulations, do you see weak shocks?
So I more or less just forgot to mention that the bow shock definitely, like things bouncing back, whether that is an exactly shock or sound wave is not quite clear, but you definitely have heating via shocks as well. How efficient this is exactly, I think, depends a bit on for me, parameters like 2D cycles, like variability of a jet, or things like that. I investigated a specific set of these parameters, essentially, just to get a basic idea. But shocks are definitely there, and they're definitely doing something. Yes.
So we are obviously not resolving the accretion disk around the
Yeah.
black hole and the immediate vicinity of the black hole inside the boundary radius. And the question is, what gives you confidence that we're not missing something big? Because why do you think we're capturing the essence of the phenomenon?
For the massive galaxies, I don't know. For the galaxy clusters, at least, in terms of where you really see cavities, I think it's quite clear that the jet itself is not the ultimate solution to the cooling flow problem, but it has something to do with the cavity and the dynamics of the cavity.
Well, my question was more about the subgrid physics.
Okay, yeah.
So how do we know that it's correct?
In the end, I would say we don't. The best, the best way to really answer this, I think, is to really try to systematically now. Also, I mean, there are a lot of, for example, IFU surveys going on, trying to trace different gas components, trying to trace their outflow properties and stuff like this, which we haven't had before, and which we also theoretically, from a model point of view, haven't really been able to constrain. And to look at these as well might give you some more clue in those directions. But you might also always have some kind of effects on smaller scales. It's a fundamental problem. I'm not 100% sure how to solve it.
The question is whether it matters
So I think once you have the situation where you have just such an enormous amount of energy that needs to get out, it doesn't matter anymore. For the question is, what is that energy? And figuring that out, I'm not sure whether that's that easy. But yeah, I think like just looking at outflows, which is something we can do now, would be a first step towards that, and see whether we can kind of, once we model these outflows, can see what these do is a good first step. I should also say this study is not targeted towards the question, for example, what drives these jets or what drive winds in the first place. So whether they are driven by radiation, whether they're driven magnetocentrifugally or stuff like this, is a very interesting question, but it's not the question I want to answer. So that might be independent of that, though needs to be investigated separately.
I have one. You only talked about like radial profiles, right? The radial heating profiles and the energy injection in the radial direction.
Mm-hmm.
But your jet is not isotropic. So how do you account for cooling in the other direction, for example?
Yep, that is one of the problems,
Right.
obviously, that immediately comes to your mind. So for the energy deposition, just by inflating a cavity, cavity is rising, everything else falls back.
Right.
This all is a subsonic process. So you actually fall back, it falls back from all directions. So you automatically get a heating in all directions, which is more or less isotropic, which is a very interesting property of that. I mean, this issue you mentioned is one of the reasons why currently heating via turbulence is a very debated thing, because the velocities involved are just not large enough to distribute the eddies. For cosmic rays, for example, it looks a bit better, but I do not have a definite answer yet to that.
So regarding your last point where were you thinking about AGN feedback in LORM-S systems, do you think if they are different, they will be like an entirely new type of feedback, or will just like of the two types that you have operating here, just like with a different set of parameters?
So the main thing that worries me currently is, like, from my current understanding of the analysis of the IllustrisTNG simulation, is like we need a kind of third mode of feedback, which is really collimated jets, which I hope not to need at some point. So I really try to have these two under control, which I should say what I haven't really talked about much is like this quasar mode feedback, which in the end in our simulations turns out not to do very much. Whether that is just a model, a statement about the model, or whether this is something that is physical remains to be also investigated, but this is not exactly what I'm working on at the moment. But I'm mainly concerned about really kinetic outflows and what they do to the surrounding. And I really don't want a third mode. I'm already unhappy with two modes. So I would be more happy if that's essentially the same thing, just a different manifestation, say because of environment or something like that.
Okay, let's spend time.
I'll go for a minute. I have a question for you. I came a few minutes late. I don't know whether you explained at the beginning, but one of your slides you have the three different mass scales up, and the dominant form of the feedback goes from one to the other, of accretion as well. What physically changes as you go down the mass scale to convert from kinetic mode to thermal mode?